This is your presenter Asloob Mudassar, and I am presenting slide number 118 of the course on laser physics. Question is, if a laser is operating in the TEM00 mode, it can still operate in a large number of longitudinal modes. Cavity length can be adjusted to select a single longitudinal mode operation, and with the use of single Fabry-Perot Etalon, a single longitudinal mode operation with a relatively longer cavity length can be realized. Discuss the physics of single longitudinal mode selection with and without Fabry-Perot Etalon. The answer is, let delta nu naught is the width of the gain profile of a laser oscillating with several longitudinal modes. For example, nu naught, nu plus minus 1, nu plus minus 2, and so on, which are separated in frequency by delta nu is equal to C over 2 times LC, where LC is the cavity length of the laser. So nu naught is the central mode, central longitudinal mode, and on the right hand side of this nu naught there is a longitudinal mode with the nu plus 1, and the nu minus 1 lies on the left hand side of nu naught. Similarly, nu plus 2 lies on the right of nu plus 1, and nu minus 2 lies on the left of nu minus 1. To increase the mode separation, delta nu. So delta nu is the difference between these consecutive modes. That is the difference between nu naught and nu plus 1. Similarly, the difference in frequency between the nu plus 1 and nu plus 2 is delta nu. And similarly, on the left hand side, the difference between the frequency between the nu naught and nu minus 1 is delta nu. Similarly, the difference of frequency between nu minus 2 and nu minus 1 is again delta nu. And similarly, we can say that delta nu is the separation between two consecutive longitudinal modes. To increase the mode separation, delta nu, LC, which is the cavity length, can be made smaller. So you see that here from equation number 1, it is evident that if you make LC smaller, then of course delta nu can be made larger. That is, the separation between the two consecutive longitudinal modes can be increased by decreasing the value of LC. Here C is the velocity of light in the numerator. When delta nu increases, then the number of oscillating modes, that is the modes contained in the gain profile, decreases. Suppose we set capital L. Here it means that capital LC in such a way, so because LC is the length of the cavity, and here this L means LC, which is the length of the cavity. If we set LC in such a way that delta nu is greater than delta nu naught by 2. So delta nu is the separation between the two consecutive modes, and delta nu naught is the width of the gain profile. So the separation between two consecutive modes should be greater than at least the half width of the gain profile. So let me show you the gain profile so that you can really understand what is happening. This is the laser gain profile. So its caption is laser gain profile, longitudinal modes, and the transmission peaks of the Fabry-Perot Etalon. So let me explain this figure. So this J is the gain profile drawn vertically upward, and nu is the frequency which is drawn along the horizontal axis. This curve, this broader curve, is actually the laser gain profile curve. The separation of this curve at full width half maximum is delta nu naught. So this delta nu naught is very important for us because we shall be doing the calculations with respect to delta nu naught also. So you see that there is one sinusoidal function, sinusoidal curve, continuous curve. this curve at the bottom. This is actually one mode, one longitudinal mode, because it is one sinusoidal frequency. So if there are two sinusoidal modes, the other mode will have a slightly different frequency than this mode. Then of course that mode will be +1 mode if the frequency is higher, but if the frequency is lower than this one, then this will be nu -1 mode. So here we have shown only one longitudinal modes. So this is a sinusoidal pattern which corresponds to the one longitudinal mode of the laser cavity. So you see that if you have only one longitudinal mode, that will lie in the center of the gain profile, denoted by the central frequency nu naught. So if you have two modes or more modes, for example, so let me fit over here other two set of modes. For example, if you have nu +1, that will be lying somewhere over here, touching the frequency axis and then going upward, touching the laser gain profile curve. So this one, for example, will be nu +1, and the nu +2 will be lying somewhere over here, because we are assuming that only five longitudinal modes are fitting into the gain profile. So -1 mode will be on this side, and -2 mode will be over here, because we are assuming that this gain profile is made up of 5 longitudinal modes. But you know that in principle there could be a very large number of modes with lying making actually this gain profile. So this gain profile is actually made up by the contribution of many longitudinal modes. Some of them lying on the right hand side and some of them lying on the left hand side, but both are lying symmetrically to each other, and the delta nu will be the separation between two consecutive longitudinal modes. So this laser gain profile is made up of many longitudinal modes, and I have not shown those longitudinal modes over here. And you know that this delta nu naught is the width of this laser gain profile at half maxima. Now I have shown some these curves dotted shown in elongated dotted lines. This curve, then the curve just close to the center again in the dotted line, and there is another transmission curve lying over here in the form of dotted curve. These curves are actually the Etalon's transmission peak curves. So these are the transmission peaks of the Etalon. That is the Fabry-Perot Etalon. So you see that one transmission peak I have shown over here, slightly deviated from the center of the laser gain profile, and of course the other two have also shown. The width of this is the transmission peak of the Etalon. It means that if you are using an Etalon in a laser cavity, then only those longitudinal modes will be selected which lie under the width of delta nu c. So if you have a longitudinal mode lying within delta nu c, that is lying within the transmission peak of the Etalon, it will be selected by the Etalon and it will oscillate within the laser cavity, and of course it will come out as and of course it will come out in the output of the laser beam also. So you see that these are, I have shown these three transmission peaks of the Etalon. It means that the Etalon, this Etalon which I have shown for the three peaks, will select three longitudinal modes. One mode will pass through the center of delta nu c, the other from the left one, and the other one from the right peak. So these are the three transmission peaks. Out of these three transmission peaks, three longitudinal modes at the maximum can pass. If they are well separated from each other, then of course they will be contributing in the oscillation of the laser beam along the resonator axis, and of course these three longitudinal modes as allowed by the transmission peaks of the Etalon, will pass through out of the laser beam in the output beam of the laser. And you will notice one quantity which I have represented as delta nu FSR. FSR stands for the free spectral range. So the free spectral range is actually the new frequency is the difference in the new frequency is the difference in frequency between the peaks between the two consecutive peaks of the transmission etalon between the two transmission peaks of the etalon, and these must be consecutive peaks. So delta nu FSR is the separation between the two peaks between the two consecutive peaks of the transmission peaks of the etalon. So this is the delta nu FSR. And you know that the each transmission peak has a full width of maximum equal to delta nu C. So if you divide delta nu FSR with the delta nu C, you will get a quantity which is called capital F. And capital F is called the finesse of the etalon or finesse of the um, Fabry-Perot interferometer. So the ratio of delta nu FSR to delta nu C will give you a quantity which is called the finesse of the etalon, denoted by the symbol capital F. And here you can see that C over 2LC is actually the separation between two consecutive longitudinal modes. If you treat this continuous curve, you can also treat it as if consisting of many longitudinal. So each peak can also be assumed, for example, as a longitudinal mode. So you can see that many longitudinal modes are now present under the laser gain profile. So you see that I have shown only very limited width of very limited height of these one, but in principle their height touches the upper peaks touches the laser gain profile. So it means that, for example, this curve will touch over here, for example over here, and if you have this curve, for example, this curve will touch the laser gain profile over here. So if you consider these as the longitudinal modes, then of course these longitudinal modes, the upper peak of these longitudinal modes will touch the gain profile of this laser profile. So touching the lower peaks will touch the horizontal axis, and the upper peaks will touch the laser gain profile. Then you can treat these modes as the longitudinal modes. So you see that now I am going to explain all these things with reference to this figure most of the time. So here delta nu, which is equal to C over 2LC, is actually the separation between the two consecutive longitudinal modes. That is the separation between nu naught and nu plus 1, or nu naught and minus nu 1, or nu plus 1 and nu plus 2, or nu minus 1 and nu minus 2. The separation between two consecutive longitudinal modes is delta nu is equal to 2C over 2LC. So to increase the mode separation delta nu, LC, which is the cavity length, can be made smaller. When delta nu increases, then the number of oscillating modes, that is the modes contained in the gain profile, decreases. So if you increase LC, then delta nu will decrease. But if you will decrease LC, the delta nu will increase. That is the separation between the longitudinal modes will increase. So if there are greater separation between between the modes, that is, if delta nu is a large quantity, then you know that very few modes will be able to fit into the laser gain profile. For example, over here, if delta nu, that is the separation between these longitudinal modes, is much larger, then only few will fit into the laser gain profile. But if it is very large, it might be possible that only one longitudinal mode will be present in the center of the gain profile, and the second modes will be lying outside the gain profile. So if they are lying outside the gain profile, they will not be oscillating within the laser cavity, and of course they will not make a part of the laser beam. So suppose that now we set the value of L. Here L means that LC. So now we set the value of the laser length cavity in such a way that delta nu is greater than delta nu by 2. So delta nu naught, you know, that is the width of the gain profile at its half maximum. And if you take the half width of delta nu naught, and if your delta nu, that is the separation between the modes, is greater than delta nu naught, then what will happen? And you tune the modes such that the central mode coincides with the center of the gain profile. The two modes, that is nu plus 1 and minus 1, will be at the far ends of the gain profile. So let me explain this condition, that is delta nu is greater than, that is the separation between two consecutive modes is greater than the half, is greater than delta nu by 2. So again you see that delta nu over here, this is the width delta nu, the full width of the gain profile. So if you take the half of this value, then suppose that this value from here to here in the center. But you know that if your modes delta nu, that is the separation between two longitudinal modes, is greater than this half width, then what will happen? Suppose that the central mode lying over here, then the other mode will be lying maybe slightly outside this laser gain profile. So it means that it might not be oscillating, or it might be oscillating marginally, because because the profile will not be totally fitting into the laser gain profile. Only a part of that one may fit into the laser gain profile. So under this condition, well, delta nu, that is the separation between two longitudinal modes, is greater than the delta nu naught divided by 2, then of course if one of the modes lying in the center, then what will happen to the second mode? And tune the modes, so if you want to tune the modes, it means that you very precisely change the length of the laser cavity. So this is what it means by tuning. So if you tune the modes such that the central mode coincides with the center of the gain profile, the two modes that because the central mode nu naught will be lying in the center of the gain profile, then the other two modes, for example nu plus minus 1, will be at the far ends of the gain profile. A laser with a moderate threshold will cut off the oscillations of nu plus minus 1. So if your laser threshold is moderate, then of course the pumping power will not be available much to pump these two modes, that is nu plus minus 1 modes, and only the central mode with the frequency nu naught will oscillate. The length of the laser cavity should then satisfy the condition, that is the LC should be less than or equal to C over delta nu naught. And this is the condition you can obtain from here. That is, if you combine these two, you can get the value of delta nu naught and LC. So LC can be connected to delta nu naught through using equation 1 and 2. So you will have, that is the length of the laser cavity should then be less than or equal to C over delta nu naught, where delta nu naught is the width of the gain profile. So if you have estimated a gain profile in your mind, you can put the value of gain profile delta nu naught over here in equation number 3, and you can calculate the proposed value of the laser length cavity. So this equation shown in figure number 3 follows from equation number 1 and equation number 2. With the equality, so if you are using an equality sign, with the equality sign, the peak value for the modes nu plus minus 1 will be half the central mode peak value. That is, their strength will be half, that is the peak corresponding to these plus minus 1 modes will have a half value, will have a half of the value corresponding to the central mode nu naught, provided we are using the equality sign over here. To bring the central mode nu naught at the center of the gain profile, mode tuning is performed by changing the length of the cavity. And Etalon, an elongation in the laser cavity by a distance lambda by 2 shifts a mode at the position of its next neighborhood position. So you see that if you have a central mode in the cavity, for example, lying along the center of the gain profile, and if you change the length of the cavity by lambda by 2, you would be able to position a nu naught at the position of either nu plus 1 or at the position of nu minus 1, depending upon you increase the length of the cavity or you decrease the length of the cavity by a value equal to lambda by 2. So an elongation in the length of a cavity by a distance equal to lambda by 2 shifts a mode at the position of its next neighborhood position. That is at the position of the next longitudinal mode. To change the length of a cavity, one of the cavity mirror is mounted on a voltage controlled piezoelectric transducer. The displacement of the mirror along the resonator axis is then controlled by applying appropriate voltages to the piezo transducer. The width of the gain profile of a typical helium neon laser, which is operating at 632.8 nanometer, is this, that is delta nu naught is equal to 1.7 gigahertz. So this is the width of the gain profile of a typical helium neon laser, which gives the length of the cavity LC to be less than equal to 17.5 centimeter. Some solid state lasers with a typical size of the order of 1 millimeter operate with a gain profile much larger than, for example, of the order of a few gigahertz. Next, we present. So you see that here up to this point we have presented longitudinal modes, separation between the longitudinal modes. Where the longitudinal modes lie, they lie under the laser gain profile, because the laser gain profile is actually constituted by the contribution of the longitudinal modes. If more longitudinal modes are present, then of course the gain profile will be broader. So this is what we have explained, the theory of the modes, longitudinal modes, the gain profile, the separation between the longitudinal modes and the width of the gain profile. Now we want to describe the condition, under what condition we can obtain a single longitudinal mode to be oscillating within the laser cavity. So next we present how Fabry-Perot Etalon can be used as a mode selective element. For single mode selection, a Fabry-Perot Etalon is inserted within a resonator cavity. A Fabry-Perot Etalon consists of transparent plane parallel plate with two surfaces having a high reflectivity R1 and R2, which we may take as R1 is equal to R2 is equal to R. That is, the two mirrors have the same reflectivity equal to capital R. And you see that I have shown the Etalon over here. This is the Etalon. That is the Fabry-Perot Etalon, or the Fabry-Perot interferometer, or the Fabry-Perot Etalon. If you want to see a detailed description of this Fabry-Perot Etalon, I have covered the detailed description in slide number 78 and slide number 79. So I would suggest that if you want to have a detailed discussion about the Etalon or the Fabry-Perot interferometer, you should consult slides number 78 or 79. So you see that these are the plane parallel mirrors cavity having mirror 1 and mirror 2, and the Etalon is placed close to the mirror 2 because we want the output beam to be coming out from the mirror 2. Here is the active medium, and you see that the width of the Etalon is represented by capital L. This is the width of the Etalon, and the width of the laser cavity, that is the distance from mirror 1 to mirror 2, is represented by capital LC. And you see that I have shifted the Etalon, that is, Etalon has been rotated, and the normal angle and the normal to the Etalon makes an angle theta prime with the horizontal axis of the resonator. So If you change the value of the, if you change the angle of rotation, you can select different longitudinal modes to be propagating within the laser resonator. So rotation of the Etalon is important in the selection of different longitudinal modes. The description of this figure is mechanism of single longitudinal mode selection using a single Fabry-Perot Etalon. Next, we present the theory by which we can understand how the selection will be possible. Assume that the Etalon's normal makes an angle theta prime with the resonator axis and the beam makes an angle refraction theta. So you see that I have not shown the angle theta. What is the angle theta? Because you see that this is the normal angle with the input beam. The Etalon normal makes an angle theta prime with the input beam. And when the light enters into the Etalon, it will make an angle which we call as a theta angle, and that theta angle will also be the angle with the normal. So the angle of refraction inside the Etalon will be angle of theta. So assume that the Etalon's normal makes an angle theta prime with the resonator axis and the beam makes an angle of refraction theta. Then the transmission maxima of the Etalon occurs at the frequencies nu n given by this equation. That is nu n is equal to n times c, where n is an integer, c is the velocity of light, divided by 2 times nr times L times cos of theta, where nr is the refractive index of the material within the Etalon, capital L is the thickness of the Etalon, and cos of theta, theta is the angle that I have mentioned over here. That is the angle of refraction inside the Etalon. And you see that I have given you the reference of this equation, that is equation number 4, to have a look at question number 78.10. So this equation, that is equation number 4, has been taken from slide number 78 and equation number 10, that is equation number 10. N takes integer values. Nr is the refractive index of the Etalon. The width of the Etalon is much smaller than the cavity length LC, that is L, which is shown in green. Green means that all the quantities which I have shown green next onward will represent the quantities related with the Etalon, and the quantities which will be shown in the red will be the quantities which will be related to the laser cavity from now onward. So here L shown in green is the length of the width of the Etalon, which is much smaller than the length of the laser cavity represented by LC. So you see that different values of different integer values n provide you an opportunity to select different wavelengths nu n. So you see that nu n can also be selected if you rotate the angle theta. This angle theta is present over here. So if you rotate the angle theta, that is you rotate theta prime. So in principle, you also change the value of theta, which is the angle of refraction inside the Etalon. So you see that if you change the value of theta, then of course cos of theta will be changed, and then you can select a different frequency nu n to satisfy this equation. To select or tune mode close to the center of the laser gain profile, a small tilt of Etalon by an angle theta prime or equivalently by angle theta is needed from the position the normal to the Etalon coincides with the resonator axis. So this delta nu, which is you already familiar, is equal to C over 2 LC, which is the separation between the two consecutive longitudinal modes within the laser cavity, is shown in red because it is related within the laser operation, gives the frequency separation. Delta nu gives the frequency separation between the two adjacent longitudinal modes. Let delta nu C shown in green. It means that this quantity is relevant to the quantity to the parameters of the Etalon. Let delta nu C is the line width of the Etalon transmission peak. So let me show you this delta nu C. You see that this is the delta nu C. That is the width of the transmission peak of the Etalon. So I shall be representing this delta nu C with green color. So that, and the delta nu FSR will also be represented in green, so that you can notice that these quantities are relevant with the theory of the Etalon. Okay, this delta nu c gives the frequency separation between the two adjacent longitudinal modes. Let delta nu c is the line width of the Etalon transmission peak. That is the width of the transmission peak of the Etalon. If delta nu, that is the separation between the two consecutive mode, is greater than or equal to delta nu c by 2, then the central mode close to the line center of the transmission peak is selected, and the two neighboring modes suffer great loss, maybe more than 50%. The discrimination between the two adjacent longitudinal modes requires that delta nu, that is the separation between the two longitudinal modes, should be at least greater than or equal to delta nu c by 2. So this is how you can discriminate between the two modes. So let me explain this one, that delta nu we require, that is the separation between the two consecutive modes should be greater than half the width of delta nu c. For example, over here, suppose that nu naught is aligned with the center of this delta nu c, that is with the center of the peak corresponding to delta nu c, corresponding to the transmission peak. So suppose that one mode, that is the central mode, central longitudinal mode, is aligned with the peak, with the transmission peak of the Etalon. Then what about the nu plus 1 and nu minus 1? It means that the nu plus 1 will be lying outside this dotted peak, that is outside the transmission peak, because over the width of delta nu, that is the width, or that is the separation between the two consecutive longitudinal modes, is greater than the half the separation of this delta nu c. It means that the second longitudinal mode will be outside this transmission curve, and similarly nu minus 1 will be lying on the left of this transmission curve. So only the central longitudinal mode nu naught, if aligned along the center of this transmission curve, will pass. The other modes, that is nu plus 1 and nu minus 1, they will not pass through this transmission peak, because we have assumed the condition that the separation between the two peaks should be, that is delta nu, which is the separation between the two consecutive longitudinal modes, is at least equal to or greater than delta nu c by 2. So this selects only one mode, one longitudinal mode. Now let me combine the two conditions, that is delta nu c less than 2, delta nu c divided by 2 is less than delta nu. I have combined these two conditions on the extreme ends. That is delta nu c over 2 is on the left one, and the delta nu in the red is on the right side. And in between the two quantities, I have placed this delta nu FSR, that is the free spectral range divided by 2f, where capital F is the finesse of the Etalon. The definition of the finesse is that it is the ratio of delta nu FSR to delta nu C. So this is the ratio, that is the ratio of delta nu FSR to delta nu C. This ratio is called capital F, that is the finesse of the Etalon. So I have used the definition of the finesse over here. So you see that this is the quantity. The two quantities in the two terms in green are related with the Etalon, and this term, which is red, is related with the separation between the two consecutive longitudinal modes. So this is related with the laser cavity. Delta nu FSR is the free spectral range, and delta capital F is the finesse of the Etalon. And you know that let me show you the free spectral range over here. You can see that this is the space between the peaks of two consecutive transmission peaks of the Etalon is called delta nu FSR. That is the free spectral range in frequency. And the ratio of this delta nu FSR to delta nu C will give you the fineness of the interferometer. So the greater the value of delta FSR, the greater the value of the fineness, the higher is the resolution of the Etalon. But you know that if f is great, if f is smaller, that is the fineness is smaller, it means that this curve, this transmission peak can come closer to this transmission peaks. That is, the two transmission peaks will be closer to each other, and the Etalon will have a poor resolution. So if delta nu FSR is greater, that is this central peak, for example, is lying outside this gain profile, and this peak is also lying outside outside the laser gain profile, and only one transmission peak of the Etalon is present within the laser gain profile, then you see that only one longitudinal mode will be selected, because we have already assumed that delta nu, the separation between the two consecutive longitudinal modes, is greater than half of the width of delta nu c. So let delta nu naught is the line width of the gain profile. This is what I have already explained. Figure 2 shows three transmission peaks of the Etalon under the gain profile, and thus three longitudinal modes, one corresponding to each transmission peak, will be selected for oscillation. So you see that this is our laser gain profile, and you see that the three transmission curves corresponding to the Etalon have shown to lie within the laser gain profile. So it means that three longitudinal modes lying under these transmission peaks will only be allowed by the Etalon to propagate or to oscillate within the laser cavity, and thus make a part of laser output beam. Because we have already assumed that our longitudinal modes are so separated that only one mode will be lying within the width of delta nu c. So only three modes will be selected. Single mode operation can only be ensured if delta nu FSR is greater than or equal to delta nu by 2. So this condition would make you to select only single mode. So let me explain this figure in the figure. So you see that if delta nu FSR is greater than, here I have shown in the figure that delta nu FSR is equal to half the value of delta nu naught. And that's why we have the three transmission peaks corresponding to the Etalon over here. But if delta nu FSR is greater than the half width of the laser gain profile, that is, if delta nu FSR is greater than delta nu naught by 2, then you see that only one transmission peak, or at least the two transmission peak, could occur in the laser gain profile, and so two longitudinal modes could be selected. But if delta FSR is even greater than delta nu FSR, or if delta nu FSR is of the order of delta nu naught, that only one transmission peak will be lying within the laser gain profile, and only one longitudinal mode will be selected. So this is the condition that we can use to select only one longitudinal mode. For example, delta nu FSR is greater than equal to delta nu by 2. Or more accurately, delta nu FSR should be of the order of delta nu naught, so that only one transmission peak lie within the laser gain profile and only one longitudinal mode could be selected. With the equality sign, there would still be three transmission peaks, provided the central transmission peak occurs close to the mid of the gain profile. But the two longitudinal modes corresponding to the side transmission peaks would have much lower magnitudes compared to the central mode. The situation can be considered as the operation of a single longitudinal mode. So you see that if you consider the equality sign over here, then of course the three transmission peaks of the Etalon will still be lying as shown in the laser gain profile. So it means that the three longitudinal modes. Suppose that this central transmission peak is lying in the center of the gain profile. Then you see that this transmission peak will be slightly shifted towards the left, and this will be shifted slightly towards the right. But you know that since gain profile is going downward on the extreme ends, it means that the longitudinal profile, longitudinal mode over here has a magnitude or has a strength much smaller than the strength in the center, strength compared with the central longitudinal mode lying over here. So these will have smaller magnitudes. That is the mode, longitudinal mode lying over here, and the longitudinal mode lying over here will have smaller magnitudes. Or ultimately, we can, on the basis of this, we can assume that effectively there is only one longitudinal mode present. But the two longitudinal modes corresponding to the side transmission peaks would have much lower magnitudes compared to the central mode. The situation can be considered as operation of a single longitudinal mode effectively. So combining the last two inequalities, we have this inequality and we have this inequality. So in this inequality, delta nu naught is not present. So then we are going to include delta nu naught by combining the two inequalities. So we have, that is the delta nu FSR, that is the free spectral range in frequency, should be at least greater or equal to half of the value of the gain width of the profile, that is delta nu naught by 2. And this delta nu FSR should be less than equal to 2 times f into delta nu. The quantities in red corresponds to the laser parameters, and the quantities in green represents the parameter related with the Etalon. And capital F is the fineness of the Etalon. And delta nu, this delta nu is actually the separation between two consecutive longitudinal modes. This delta nu naught is actually the width of the gain profile. So if this condition is satisfied, that delta nu FSR is greater than the half width of the gain profile, but less than 2 times f times delta nu, then of course you would be able to select only a single wavelength, a single longitudinal mode, for example, in an effective sense. So here you can write that delta nu naught divided by 2 is less than equal to 2f times delta nu. I have skipped the middle term, which is the delta nu FSR. So skipping the middle term, I can write this one as shown. So you can now put the value of delta nu, which is the separation between the two modes, is given by C over 2 times LC. So the separation between the two consecutive modes is given by C over 2 LC. And you can solve this equation for the value of LC. So LC becomes less than equal to C over delta nu naught times 2F, where F is the fineness of the interferometer. So you see that this is the condition on the length of the laser cavity. So your length of the laser cavity should be less than this quantity on the right hand side if you want to select only a single longitudinal mode. Using single longitudinal mode using single Etalon. So this provides a check on the length of the laser cavity for single longitudinal mode operation or selection, which shows that the cavity length can still be increased by a factor of 2f. You see that you can see a factor of 2f over here. So placing an Etalon in the laser cavity, it has allowed you to increase the length of the laser cavity. So if you are not using a Etalon, then you see that 2f will not be present over here. Then LC will be less than equal to C over 2 delta nu naught only. So there will be a strong constraint on the value of LC. But if you use a single Etalon, then you can multiply the right hand side with 2f. So the length of the cavity is increased because it allows you the right hand side being greater multiplied by 2f will allow you to use an increased value of the laser length cavity, which is always desirable because the length of the laser cavity increased in the length of the laser cavity will ensure greater output optical power from the laser. So which shows that the cavity length can still be increased by a factor of 2f of the cavity length without Etalon for single mode operation. So without using an Etalon, the constraint on the length of the laser cavity will be less than equal to C over delta nu not only. But if you are using Etalon, it will be C over delta nu naught multiplied by 2f. If the cavity length does not satisfy the condition given by equation number 7, a second Etalon can also be used. The thicker Etalon discriminates because then we use two Etalons. One is slightly thicker than the other. So we have called it a thicker Etalon. The thicker Etalon discriminates between two adjacent modes, and the thinner Etalon chooses the transmission peak. In the presence of the two Etalons of the same fineness f, it can be shown that the length of the laser cavity will then be equal to, so LC will be less than equal to C over delta nu naught times the square of 2f. So you can compare it with the previous result. You see that if you are using one Etalon, you have 2f over here. But if you are using two Etalon, you have the square of 2f. So it will provide this equation 8 provides you a more more flexibility to increase the value of the laser cavity or the length of the resonator. So let me summarize. So if 2f is not present, then LC is less than or equal to C over 2 delta naught is the condition to select a single mode without using Etalon, but with a limited size of the cavity. But if you are using a single Etalon, you should multiply the left hand side with 2f, where f is the fineness of the Etalon. So the right hand side now allow you to have a flexibility with the increased value of LC. But if you are using two fineness over here, two Etalon over here, you have a quantity on the right hand side represented by the square of 2f. So you have a flexibility to use longer laser length cavity. So we can summarize the results of the single longitudinal mode selection as follows. The length of the laser cavity LC is constrained by this equation if you are using no Etalon in the laser cavity. But you are still selecting a single mode, but with the limited output optical power because you have a limited size of the laser cavity. But if you want to increase the laser cavity, you are using an Etalon, a single Etalon of fineness f. Then of course LC can be increased beyond the value of C over 2 delta naught, but up to the value of C over 2 delta naught multiplied by 2f. So this is with the use of single Etalon. And if you are using two Etalons together, then you have more flexibility to increase the value of a laser cavity LC. Then LC can be increased from the value of C over delta nu naught multiplied by 2f to the value of C over delta nu naught times the square of 2f, where f is the fineness of the Etalon. So you see that this is a summary of the discussion that we have done. So this is the end of slide number 118.